All right, so in this one, we have a graph of the force versus displacement. I haven't read the problem yet, but we have a force versus a displacement graph. And we want to be able to extract information about the work. Okay, so the force applied by the spring is described by the graph below. What is the work done by the spring when it returns to its natural length, i.e. when the block moves from 0 to 5 centimeters? Okay? All right, so we want to think about what the work done by the spring here is there. Okay, so let's just kind of just draw a picture, so to make sure we understand like the motion of here to connect it to the graphs. All right, don't just go straight into a calculation. Think about it. So if we've positioned it at 0, so at 0 centimeters, this is the force. That means like this is x equals 0, and I think they're saying that the relaxed length here is 5 centimeters. X equals 5 centimeters. So we're going to... Actually, I think it's... sorry, it's compressed. My bad. So we've squeezed the spring. So let's draw a compressed... Well, okay, let's just imagine it's compressed here. And then the natural length is over here. This is x equals 5 centimeters. So this is where the spring would like to be if there was nothing pushing on it. So let's think about the direction. Let's draw the free body diagram. What is the direction of the force on the spring during this motion? So we have, well, let's think about all the forces. We have gravity. We have normal force from the surface. Let's just assume it's a smooth surface. There's no friction. And then the spring force is going to act this way. So when we go from 0 to 5 centimeters, the spring force is to the right. So we want to think about that area. Now, you cannot just do the spring force times the displacement. Why? Because the spring force is changing during the time, so we cannot just use the force times the displacement. Because the force is not constant, we have to do this area. This area is going to give us the work, force, and the displacement. So you're going to do the area. It's 1/2 the base. Now be careful here. This is in centimeters. We want to convert that to meters. That's 0.05 meters. You divide by 100 to go from centimeters to meters. And then the height of this is 25. So this is the area of a triangle. So that's 0.5 times 0.05 times 25. That area is going to be 0.625 joules. Okay, so that's the work done by the spring here, 0.625 joules. What is the work by the spring as it stretches 5 centimeters beyond the natural length? I want to push this from 5 to 10. So now it's going to go from here to here. Okay, so we're going to go from there to there. Now what's going to happen is the spring force is this way during the motion, because now we've stretched the spring. It's trying to get back to its relaxed length. But again, the spring force is going to vary, but you're going to have negative work because you know the displacement is to the right, and so the work should be negative. And that is shown by a negative area here. Okay, this area also being negative. Okay, so this area is going to equal to 1/2 the base, which is going to be, again, 5 centimeters. From 5 to 10 is 5 centimeters, which is 0.05 meters. And the height is negative 25. So it's going to be negative 0.625 joules. It's going to be negative 0.625 joules. And it's negative for two reasons. One, the area is under here. And then also because the spring force is opposite the direction of the displacement. So that makes sense that the work would be negative. What is the work done by the spring as it moves the block from 0 to 10 centimeters? So if we look at the total work, the work here and the work there, this is going to be 0 joules, because it's going to be the 0.625 plus the negative 0.625, which would give us 0.